with the process of aligning the antenna in a Ceragon microwave installation project. The agenda of our module consists of the following topics. Why do we align the antenna? What is the relevant hop data? What is the use of the column support of pole mount? How to use the stop ring and what for? The antenna's course alignment. What are the tools needed for antenna alignment? What are the azimuth and the elevation of the antenna? What is a radiation pattern? The main and side lobes. Antenna alignment, cross-polarized, and spatial diversity scenarios. Before you begin to align antenna, it is important to know that a good installation practice has been followed and antenna is correctly set up per manufacturer's instructions. Always have the manufacturer's notes or installation guides available and make sure to read and understand them. First of all, why do we align the antenna? Antennas are aligned to achieve the maximum received signal strength or input level at each end of a radio hop. This is to be done in correlation with the link budget document issued by the radio planning team. Next, let's look at how to align antenna, generally. Always, your first step should be to study the bulletin delivered with the antenna, in order to become familiarized with the particular panning operation for the antenna. Keep in mind they are not all the same. Panning is the operation carried out to align an antenna through azimuth positioning, done in the horizontal plane, against the Earth's true north. Elevation positioning, done in the vertical plane for maximum alignment to the antenna on the other end. The antenna bulletin will normally list what the minimum tools required in order to correctly pan the antenna. Aligning an antenna is not a very simple matter, just using a few tools. Difficulties can arise trying to establish the signal. When these difficulties appear, having the ability to interpret the received signal can mean all the difference between having a successful installation or a deeply frustrating day. We will treat all of these difficulties in this module, so you can be prepared for any scenario. What is the link or hop data? First of all, the hop is the radio link connection between two antennas and network elements, one at each end of the link. The hop data is all of the relevant data per each side of the link. When setting the radio hop, remember that geographical, physical and performance characteristics will be unique to each station and antenna. Let's take an example of link data, on a link to be installed between site A to site B. Per each site, the geographical coordinates are used for positioning of the antenna. That gives you the location of the tower and the antenna for site A. You can look for these locations on Google Earth to understand where the tower is. Per each site you see data about the direction of shooting, the azimuth of the antenna in correlation to the Earth's true north. Keep in mind the concept of magnetic declination discussed in our previous modules. Next, per each site location, you can see the antenna's angle of elevation. In the next row, there is information about the polarization being used. The final row shows the planned received signal level to be obtained on each side of the link. This can be symmetrical, like in our example, or not. There are two rows for data for the space diversity signal, which is not used in our link, for they contain no data. To check the verticality of the pole mount, always use a precise, good brand, spirit level to check the verticality on multiple sides of the pole mount. If your pole mount is not vertical, this will add avoidable complications during alignment of the antenna. So what happens if the pole mount is out of vertical plane on one facet, like in this example? With the pole mount leaning back towards the tower, verticality out one facet, the feed horn will respond by tracking the lines of travel shown above. Consider the dot spot as the main lobe of the other side antenna, while the red spot is the alignment of your main lobe on the near end antenna. This backwards position will not allow for the received signal to be at maximum strength. Therefore, antenna alignment will become more complicated, if not impossible, when the pole mount verticality is incorrect. The stop ring usage. First of all, we remember discussing the aim of the stop ring, being used for initial antenna support, before the final mounting position has been found. Stop rings are normally delivered together with larger antenna and must be fitted to the column, before hoisting the antenna up. The stop ring provides a platform for the antenna when panning and will prevent the antenna sliding down the column. If the antenna slides downwards, this could damage the installed waveguide. The stop rings can also be used to slightly adjust the vertical position of the antenna up or down the column to improve side strut installation. With most of the smaller antennas, stop rings are not needed as the azimuth and the elevation adjustment operates independently from the antenna mounting bracket. However, any course alignment error outside the antenna's adjustment range would require the mount bracket to be loosened. Before you loosen this, fit a temporary stop ring. Carry a spare in your vehicle, as a good practice from experienced installer teams. Azimuth and elevation range data. Please take a look at the table on the right side. Note how the adjustment range for azimuth and elevation diminishes as the antenna diameter increases. This table is presented as a guide only. Always check the antenna adjustment range from the installation bulletin provided by the antenna manufacturer. Now, let's speak about the course alignment of the antenna. The adjustment range of an antenna, in degrees, reduces significantly as the diameter increases. Therefore, it is important to be as accurate as possible when setting out course alignment of the antenna using a magnetic compass. Remember that used wrongly, a magnetic compass can produce errors of many degrees that will complicate and prolong the time needed to align the antenna. Confirm magnetic declination for your area of the world and adjust the compass and bearings accordingly to that map. Move away from the tower, some 50 meters, to avoid any interference from the metal structure, and confirm true north from compass and magnetic declination. Then rotate towards the actual azimuth, according to the plan. Once correct azimuth has been established, place a mark on that point, then turn 180 degrees to face the tower. Tie an indication rope between the marker and the tower. Make sure that the rope is visible from the top of the tower. Standard rigging rope will normally be visible from the top of most towers. One person in the tower should bring the antenna into alignment with the rope. Carry out this same procedure with the opposite antenna at the far end. Notes: never, ever cut the side strut until the antenna is finally aligned in its confirmed final position. To avoid errors, do not attempt to use a magnetic compass when working. Around or inside the tower, as magnetic deviation will be considerable.
Hey, I'll beat you.
Next, let's consider the vertical alignment. After course azimuth has been established, bring the antenna into vertical position using a spirit level against the annular ring, or other frame, at the rear of the antenna. Make any necessary adjustment via the elevation bolt. This procedure must be carried out with the antennas on both sides of the hop before beginning final alignment. The antenna is now set and ready for final alignment. Fix the side strut or side struts and secure these to the tower. Not every antenna works out easy to align, sometimes consuming several hours on a particularly bad day. Therefore, before beginning the alignment, using a pen with waterproof ink, mark the starting position of the antenna on the azimuth, side strut, elevation bolt or column. So, if you run into difficulties, this will make it possible to return exactly to the original starting position. For reference, when aligning the antenna, as each side lobe is encountered, use a pen to mark their position on the adjustment bolt. Alternatively, you could use the lock nuts as markers for each position of the side lobes. Antenna alignment, preliminaries. Before you start, ensure the following are prepared and checked. The line of sight. No obvious obstructions that can impede the antenna's line of sight are visible to you. Examples: trees that have grown, buildings that were raised from the previous visit on site, even water bridges that were not taken into consideration. The antenna pole mount is vertical on two planes at 90 degrees apart. The stop ring is installed and secured in place, if it has been part of the antenna kit. Antenna is carefully course aligned along a magnetic bearing to the facing antenna. Antenna was brought into vertical position using a spirit level. There are no obstructions that can hinder panning the antenna or obstruct the waveguide. There is sufficient space at the back of the antenna to allow free movement of the waveguide. You could even use a flex twist waveguide as a temporary arrangement. The fixed side strut are loosened to allow movement. The feed horn polarization is the same at both ends of the link. Where applicable, the better side is set and the feed horn port is leveled. Let's look at the tools you will use for the final part of the antenna alignment. As a minimum, the following tools should be available to the installer team. Working digital multimeter with test leads. A BNC connector with 2 banana test connectors. Your spirit level. Spanners fit for the bolts sizes. To know the exact sizes, refer to the installation bulletin provided with the antenna and pole mount. You need binoculars. These are useful for identification both of far station and obstructions along the way. Note, when aligning space diversity, SD, antenna via the radio unit on a branching box, a length of single pair cable should be available. This permits extending the digital multimeter down to the diversity antenna. During installation, it is important to understand how to protect the waveguide, because the team might be fully focused solely on establishing the signal. It often happens that the team forgets about checking what is happening with the waveguide during all this time. As general notes, be aware of these issues. Waveguide can easily become stressed and may even kink where it meets resistance at the pole mount, tower member, or is restrained by hanger brackets. The most vulnerable part of the waveguide assembly is where the waveguide meets the rear connector, close to the antenna. Resistance can increase considerably where force occurs along the waveguide's horizontal plane. Waveguide runs should be planned and installed to ensure there will be no conflicts at the alignment stage of the antenna. During antenna alignment, remember to loosen a sufficient number of hanger clips or standoff support to ensure the waveguide has free movement. If hanger clips would most likely be used for vertical support along the tower, a special standoff support needs to be achieved or constructed for each half a meter of waveguide left in horizontal plane, between antenna and tower. Continuously check that the waveguide has not become stressed or has run up against an obstruction. Before commencing alignment, confirm the feed horn is leveled. If the feed horn is not leveled, bring it into level using a spirit level on the top of the waveguide flange. Do this procedure for all antenna feed horn at both sides of the hop. Then, loosen the feed horn retaining bolts sufficiently to allow it to rotate smoothly by hand. Take care not to damage the guide. To do that, never use force or any tools like a wrench on the copper guide to increase leverage, but do it by hand. After the level has been reached, remember to tighten all of bolts back to the original torque. Now, let's prepare for the azimuth alignment. Fit a stop ring. With this antenna design, the stop ring can be positioned at 1A or 1B. For most antennas it will be fitted at the bottom, 1B. Loosen U-bolts 2A and 2B. Note that you should loosen U-bolts sufficiently to allow the antenna to rotate around the column. Some frictional resistance must be maintained. If loosened too much, there is possibility of signal loss when retightening the U-bolts. Loosen the pivot bolt where the strut links to the antenna frame at 3A. Loosen the 2 locking bolts to allow the side strut to move smoothly through the strut clamp assembly 4A and 4B. These 2 outer lock nuts can be run along the threaded rod to temporarily mark positions of the side lobes. The midpoint will be approximating the main lobe. As a tip, for best control when fine-tuning azimuth and elevation, use 2 spanners simultaneously, while monitoring signal strength via the multimeter at all times. Apply the same 2-spanner method when tightening the lock nuts back. Next, to prepare for elevation alignment, first off, start by locking down the azimuth position. For this, use the steps described between 2A and 4B from the previous slides. The antenna illustrated here has 2 elevation bolts in positions 5A and 5B, but only one needs to be used for adjustment. Either bolt can be used. Remember that the other elevation bolt should be fully loosened to allow free movement of the antenna. In our example, we are using the top bolt, 5A, for elevation panning. At position 5A, run back lock nuts and adjust the 2 inner nuts. At position 5B, run back all the nuts to loosen the elevation bolt freely. Next, loosen bolts at positions 6 and position 3B, in order to allow the antenna to rotate through vertical position. Monitor the signal level constantly with the digital multimeter and make reference points for the received signals. Use the same two-spanner method when fine-tuning on the elevation bolt. Tighten bolts incrementally. Remember that sometimes you need to move less than a full bolt rotation for best signal. Once maximum signal level is achieved, get ready to lock the position in place. For locking down the elevation, tighten the bolts in reverse order, starting from 5A then 5B, then 6, then 3B. Next, to prepare for elevation alignment, first off, start by locking down the azimuth position. For this, use the steps described between 2A and 4B from the previous slides. The antenna illustrated here has two elevation bolts in positions 5A and 5B, but only one needs to be used for adjustment. Either bolt can be used. Remember that the other elevation bolt should be fully loosened to allow free movement of the antenna. In our example, we are using the top bolt, 5A, for elevation panning. At position 5A, run back lock nuts and adjust the two inner nuts. At position 5B, run back all the nuts to loosen the elevation bolt freely. Next, loosen bolts at positions 6 and position 3B, in order to allow the antenna to rotate through vertical position. Monitor the signal level constantly with the digital multimeter and make reference points for the received signals. Use the same two-spanner method when fine-tuning on the elevation bolt. Tighten bolts incrementally. Remember that sometimes you need to move less than a full bolt rotation for best signal. Once maximum signal level is achieved, get ready to lock the position in place. For locking down the elevation, tighten the bolts in reverse order, starting from 5A then 5B, then 6, then 3B. Maybe the most important tool during alignment is the BNC connector that correlates receives signal strength indicator, RSSI, to a specific voltage. To use this, just remove the dust cap from the RSSI port, on either Evolution or RFUC radio and fit in place a connector type BNC to two banana connectors. Then connect the digital multimeter to observe the voltage reading at the BNC port level. The voltage reading has a direct correlation to the received signal strength in decibel. To understand the correlation, see this RSSI diagram. Number after decimal point shows conversion from receivable. A volt 0.48 volts means a received signal level on the radio receiver of minus 48 decibels. A plus minus 2 decibels variance should be acceptable. Once the reading is done and the signal level is obtained per your plan, alignment is correct. Put dust cap back once antenna alignment is done. If there is a need to install a branching box for a space diversity, maybe the most important tool during alignment is the BNC connector that correlates receives signal strength indicator, RSSI, to a specific voltage. To use this, just remove the dust cap from the RSSI port, on either Evolution or RFUC radio and fit in place a connector type BNC to two banana connectors. Then connect the digital multimeter to observe the voltage reading at the BNC port level. The voltage reading has a direct correlation to the received signal strength in decibel. To understand the correlation, see this RSSI diagram. Number after decimal point shows conversion from received signal level. For example, a voltage of 1.48 volts means a received signal level on the radio receiver of minus 48 decibels. A plus minus 2 decibels variance should be acceptable. Once the reading is done and the signal level is obtained per your plan, alignment is correct. Put dust cap back once antenna alignment is done. If there is a need to install a branching box for a space diversity installation, aligning a space diversity antenna is exactly the same process as used for the main antenna. However, it's more convenient to use a digital multimeter down at the diversity antenna level. To do this, simply run a length of single pair cable, slightly longer than the diversity spacing, from the upper branching box unit down to the diversity antenna level. You should have such a cable prepared as per antenna distance, but a 15 to 20 meters of single pair cable would cover most installation needs. Something to keep in mind while adjusting the antenna elevation. When aligning antenna, you need to know the angle of elevation between two facing antenna. While this may not be significant over longer hops, it can become an important issue over short hops. Knowing where to look for the signal above or below horizontal can be a considerable time saver. Check the link budget for this information. Let's consider the received signal level. Attaining the signal strength exactly as planned is not always possible under actual field conditions, due to all of the factors discussed in the module about radio propagation. However, a maximum signal strength of a transmission is always obtainable. This is the signal level that technicians must establish to ensure optimum system performance across the radio link. Let's speak about the radiation pattern of a microwave antenna, to understand the terms of main lobe, peaks, side lobes and decibel. Good interpretation of the received signal can save technicians considerable time when aligning antenna. First of all, if you look at the lower right side of the screen, you will see a diagram showing a 360 degrees view of a microwave antenna radiation pattern. The red point is where most of the energy of the transmission is directed. The green zones are where the lowest concentration of energy happens, and the orange and yellow zones are positions where there is some energy, but considerably less than the main red lobe. The antenna is a passive amplification device, which, by design, is able to focus and amplify most of the energy of the RF signal coming from the ODU into a very precise fascicle. That point is called the main lobe, but there are also side lobes, first and second side lobes on each side, both horizontal and vertical. These side lobes are often mistaken by the installation team as main lobe, especially because during alignment, equipment is set to maximum transmit power. The same is true for the antenna on the other end. To better understand this, observe the changes in received signal level as the antenna is panned in our left side animation. Consider the red pattern with the main beam point as the maximum signal receiving point, that gets panned as the antenna gets panned onto the far end incoming radio signal from the other antenna. You can see that once we are past the exact main beam from the other end, the received signal level starts to decrease. As we pan the antenna even more, we get even less received signal level. Some increases will be observed as we move the panning antenna through the peaks of the side lobes, but they will be far from the planned level. Understanding this animation can provide valuable information to where the receiving antenna is pointing relative to the transmitting antenna. Again, when doing the panning, you will see the multimeter voltage reading dropping or increasing as the antenna pans through better or worse incoming signal. The best signal is obtained from the main lobe, and that is where the lowest voltage on the multimeter will be observed. Most antennas have a symmetrical radiation pattern, so if you pan the receiving antenna through the two first side lobes, in between them, you will have your main lobe and get according signal information. If you pan through the first and second side lobe only, there will be a high difference in the signal reception levels, so you can assume that the main lobe will be on the other panning direction. Once antennas at both ends of the hop have been aligned, the received signal should be within 2 to 3 decibels of the calculated signal level. Let's speak about the beam width. Please observe in the displayed table the difference between the gain at the center of the antenna and the -3 decibels gain that you get when rotating the antenna a number of degrees. 3 decibels less directivity power means half of the power of the antenna's directivity. In our highlighted example, you can see that the antenna's maximum directivity is at the center focal point. Traveling a mere 1.5 degrees of rotation would mean losing 3 decibels of power, half of the power. So after less than 0.8 degrees on one side or the other, you lose half of the signal strength, for a 1.8 meters antenna, in 7 to 8 gigahertz frequency. To put things in perspective, a 1.5 degrees of this antenna rotation means a total distance traveled by the antenna of 1.5 millimeters. Considering the 1.8 meter diameter of the antenna, a 1.5 millimeter distance is almost insignificant, but highly significant in signal strength. During antenna alignment, it is important to distinguish between which are the side lobes and which is the main beam of the other side's transmission. Let's take some example readings that could be found on the multimeter during antenna panning. About the antenna elevation alignment. Determine from available data if the antenna should be above or below horizontal plane, then pan the antenna up or down in that direction. With the horizontal side lobes and main beam having already been established on the azimuth track, it should not be necessary to find the side lobes along elevation. Just fine-tuning to the maximum received signal strength should do the trick. Continue fine-tuning as necessary until the maximum received signal has been established. If the vertical angle to the facing antenna is large, it will be necessary to incrementally adjust the angle of elevation, possibly repeating azimuth panning several times before the maximum strength signal is established. Preparing for final alignment while installing a space diversity system. For a 1+0 radio link, with a single antenna at each tower, simply disregard references to the space antenna. Use the main antenna to transmit the aligning signal. The receiving antenna, which is the antenna that is being aligned, should have its signal transmission muted to avoid any interference from crossover. In the first stage of antenna alignment, the only transmitting site is Site A. Site B receives only for both main and space diversity antenna. Both sites should be manned by technicians and riggers. So Site B is in the process of being aligned. In the case of a space diversity system, both main and space diversity antenna are to be aligned to the Site A main antenna, which is transmitting. In the next step, following initial alignment done on Site B, do the following. Mute the transmission on Site A. Unmute or start the transmission on Site B towards Site A. Start aligning Site A for main and diversity antenna. Connect a digital multimeter to the RSSI BNC connector on ODU unit of the main antenna to monitor the received signal strength. This can be done via reading the RSL level on the IDU, but can be done faster with the multimeter. Align the main antenna towards Site B to receive best input level. Still on Site A, align the space diversity antenna towards Site B to receive best input level. For both antennas, follow the alignment process described earlier and align both the main antenna and the space diversity antenna towards the main antenna from Site B. Please note that the space diversity antennas on Site A and Site B will not transmit. On Site B, the only active transmission should be active main antenna. Once Site A has been finally aligned, with optimum received signal strength, again, move to Site B for the final alignment at Site B. Again, Site B transmission should be muted. This process is exactly the same as described earlier in first stage antenna alignment, with one exception. At this stage, the maximum received signal strength across the link should now be obtained. Once this signal level is obtained, the final alignment is done. Let's consider the cross-polarization systems and speak about cross-polarization adjustment. From the common channel dual polarization and XPIC concept explanations, we now know about cross-polarized interferences and how these are used to double the capacity of a link. Following the final alignment of antenna both sides of the link, the feed horn should be optimized for correct horizontal and vertical polarization to achieve maximum cross-polarization discrimination. This is performed using a spirit level. Final control. When all adjustments are performed, check that the input level agrees with the one theoretically calculated from your plan. If the input level is too low, adjust the antennas once more. Finally, ensure that all bolts, nuts and stays are properly mounted and all hanger and standoff support are secured. Before leaving the site, always ensure that the radios at both sites are correctly configured to transmit and receive and that there are no known issues left unsolved. Ideally, at this point, the elements should have network visibility confirmed by the Network Operations Center. The agenda of our module was comprised of the following topics. Why do we align the antenna? What is the relevant hop data? What is the use of the column supportive pole mount? How to use the stop ring and what for? The antenna's course alignment. What are the tools needed for antenna alignment? What are the azimuth and the elevation of the antenna? What is a radiation pattern? The main and side lobes. Antenna alignment, cross-polarized, and spatial diversity scenarios. Thank you for your attention.